the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a second video on a series about diagonalization of symmetric matrices. The previous video was just a gentle introduction to what a symmetric matrix is, and then a little bit of a preview of where we're going in this video. So let's start here with Theorem 1. If we're given a symmetric matrix, then any two eigenvectors from different eigenspaces, that's kind of important, are orthogonal automatically. Now, it's going to require a little bit of a conversation here about what does it mean for two eigenvectors to be from two different eigenspaces. Let's start by recalling that the eigenspace of a matrix is the null space of A minus lambda I. And this theorem is not talking about, well, what if the eigenvalue of 3 generates an eigenspace with a two-dimensional basis? It's not talking about that because those two vectors from that eigenspace, those two linearly independent vectors from that eigenspace, are not from different eigenspaces, they're actually from the same eigenspace. So this theorem specifically is talking about, well, what if we have eigenvectors from distinctly different eigenspaces, that is generated by distinctly different eigenvalues? Now, I will say that the eigenvectors that generate your eigenspace for a given lambda might just be orthogonal to each other. However, this theorem is not stating that if you have an eigenspace, a single eigenspace generated by lambda equals 3, for example, that you can guarantee those two eigenvectors are immediately orthogonal to one another. You can't guarantee that, actually. So let's go ahead and just move forward with the proof, assuming that we have distinct eigenvalues generating different eigenspaces. And we want to prove that the eigenvectors from those different eigenspaces have to be orthogonal. And this just encapsulates what I've been saying. Thus, if eigenvectors are from different eigenspaces, then their associated eigenvalues must be distinct, not the same. Now let's start the proof. Let A be a symmetric matrix. And we're going to suppose that we have a couple eigenvectors. We're going to keep it as general as possible. So suppose that V sub I and V sub j are eigenvectors with associated distinct eigenvalues lambda sub I and lambda sub j, respectively. Again, they are not the same eigenvalues because we don't want to talk about vectors from the same eigenspace generated by the same eigenvalue. We want to talk about eigenvectors from different eigenspaces, that is, generated from different eigenvalues. Well, if that's the case, then if you take the dot product of those two vectors, well, notice what I did here. I just wrote that dot product of V sub I and V sub j as still the dot product of V sub I and V sub j, but with lambda sub I over lambda sub I. Now, lambda sub I could be 0, so we have a little bit of a wonkiness here. Maybe we'll be able to fix that as we move forward. We'll find out. Let's go ahead and move forward on this one, though. That can be rewritten as 1 over lambda sub I times lambda sub I V sub I dotted with V sub j. Nothing really crazy there. But we happen to know that since lambda sub I is an eigenvalue with the associated eigenvector V sub I for the matrix A, then lambda sub I times V sub I is actually A times V sub I. And we also know that a dot product is just a transpose of the left vector times the right vector. That's what I have right here. Using the properties of the transpose, we could rewrite this as V sub I transpose A transpose V sub j. But remember, there's something we're assuming about A here. A is symmetric. What does that mean? It means A transpose is actually equal to A. So I'm going to trade out that A transpose for an A. And remember, A times V sub j here is just a vector. And so you can think of this as the dot product of V sub I with the vector A V sub j. Now that we have that down, remember, A times V sub j is going to be lambda sub j V sub j, because again, V sub j is an eigenvector with associated eigenvalue lambda sub j. I can factor out that constant, and I get to this guy right here. Now, what is that telling us? Well, it tells us that the dot product of V sub I with V sub j is just the ratio of lambda sub j to lambda sub I times the dot product of the vectors v sub I and v sub j. But one thing that we stated from the get-go is that these eigenvalues have to be distinct. They're not the same values. So if this dot product is equal to that product times the dot product, well, if that's true, that can only be true in one of two cases. First, if the ratio of these two eigenvalues is 1, that is, if lambda sub j is equal to lambda sub I. However, that's just not the case. We already know those two eigenvalues are distinct. And so the only other way for these two to be equal is if the dot product itself is just 0. And thus, those two vectors must be orthogonal. Now you may say, but hold on. What if lambda sub j is equal to 0? Well, we know that lambda sub I can't be equal to 0, but what if lambda sub j is equal to 0? Well then, that means, since it's equal to 0, that means this dot product must still be 0. And then you fix it and you say, okay, fine, but what if lambda sub I is 0? Well, that causes a problem, right? Or does it? Because if lambda sub I is equal to 0, I would just rewrite this entire proof starting with lambda sub j divided by lambda sub j, and in the end, we would get to lambda sub I over lambda sub j, and if lambda sub I is 0, then that numerator would be 0, and again, the dot product would have to be 0, and therefore those vectors would have to be orthogonal. So I guess the point is, this dot product will be 0 no matter what. So these two vectors, eigenvectors that is, from completely different eigenspaces must be orthogonal. Now let's talk about what it means to be orthogonally diagonalizable. Well, that's hard for me to say, so I'll try not to say it too much, but a matrix A is said to be orthogonally diagonalizable if there is an orthogonal matrix P. Remember, an orthogonal matrix is a matrix whose columns are not only orthogonal, they're orthonormal actually. So a matrix is said to be orthogonally diagonalizable if there is an orthogonal matrix P and a diagonal matrix D such that A can be decomposed into P times D times P transpose, which is P times D times P inverse, because P, again, is actually an orthogonal matrix, and if you have an orthogonal matrix, P transpose is equal to P inverse. Well, great, that's a wonderful definition, but I don't really know how we can guarantee we have an orthogonally diagonalizable matrix. Like, you would imagine that you would have some type of rule that says, oh, by the way, any matrix of this form is orthogonally diagonalizable. That is, you could decompose that matrix into a product like this where P is an orthogonal matrix. Well, we actually have a theorem. Theorem 2 tells us that a square matrix is orthogonally diagonalizable if and only if it is symmetric. So if I hand you a symmetric matrix, you immediately know it can actually be written as the product of three matrices where the first matrix, P, is an orthogonal matrix, the second matrix, D, is a diagonal matrix, and then finally, P transpose, which is actually just the transpose of P, which by the way is actually equal to P inverse because P is orthogonal. Likewise, if you are handed a matrix and somebody says, by the way, this is orthogonally diagonalizable, then you know that matrix must be symmetric. So here we are with a single example, because that's really all you need when you see this topic, a single example. They want us to decompose this into an orthogonal matrix times a diagonal matrix times the transpose of that orthogonal matrix. So orthogonally diagonalize this matrix. It goes all the way back to finding the eigenvectors and the associated eigenvalues. So let's start there. And we get down to this right here, and we can see that solutions to this characteristic equation are going to be -1 and 2. -1 has multiplicity 2. So we have that written down here. Now let's go ahead and find the associated eigenvectors. Notice those two eigenvectors are linearly independent. We had two free variables in this equation right here, or in that system, I suppose you could say. So we get two linearly independent eigenvectors, which is exactly what we want. We like the multiplicity of our eigenvalue to match the number of basis vectors for our eigenspace. Luckily, we've got that here. But notice something about these eigenvectors, which I should write them maybe over to the side here. I'll write them off to the side, over to the right-hand side. Notice those two eigenvectors are not orthogonal to each other. And so you might be wondering, wait a second, doesn't that contradict the theorem that we just wrote down? I mean, we have a symmetric matrix. That's totally the case in what we're looking at. By the way, I didn't make a big stink about that, but our matrix right here is definitely symmetric. It's a mirror image about the main diagonal right there. So it is totally symmetric matrix. But then why aren't those two eigenvectors orthogonal? Well, this theorem says if your matrix is symmetric, which our matrix is, then any two eigenvectors from different eigenspaces. In other words, they have to be associated with different eigenvalues. Well, the two eigenvectors that we got right now, they're associated with the same eigenvalue. That is, they're in the same eigenspace. So we cannot apply that theorem here. These vectors need not actually start orthogonal to each other. However, we're going to force them to be in a few minutes. Let's go ahead and deal with lambda sub 2, which is 2. All right, I did some relabeling there. So because lambda 1 was negative 1, I said the eigenvector v sub 1 comma 1, in other words, the first linearly independent eigenvector associated with lambda sub 1 is negative 1, 1, 0. The second eigenvector associated with lambda sub 1 is going to be the other linearly independent eigenvector here, negative 1, 0, 1. Now, lambda sub 2, being 2, gave us the eigenvector v sub 2, which is 1, 1, 1. Something you need to note about v sub 2 versus v sub 1, 1 and v sub 1, 2. V sub 2 is orthogonal to both of those vectors. Do the dot product with v sub 2 against v sub 1, 1. You get negative 1 plus 1 plus 0, or in other words, 0. So v sub 2 and v sub 1, 1 are definitely orthogonal. And take the dot product of v sub 2 with v sub 1, 2. You would get negative 1 plus 0 plus 1, which again is 0. And therefore, they are orthogonal. This group of vectors right here and this vector right there are from completely different eigenspaces. And by theorem 1, they have to be orthogonal, and they are. Now, normally we would say, okay, well, I'm going to build that matrix P and I'm going to throw into its columns there the eigenvectors for A. However, we're going to do a lot of specialized work here because the reality is those columns need not actually be the eigenvectors. They just have to be the vectors that will span the eigenspace generated by those eigenvectors. So you do not need P to be, oh, this eigenvector v sub 1 and eigenvector v sub 2 and eigenvector v sub 3. Instead, you can say, listen, I need my columns to span the given eigenspaces. Now, I already have that v sub 2 is orthogonal to v sub 1, 1 and v sub 1, 2. So all I'm really going to need to do is orthogonalize these two vectors right here. So we're going to use the Gram-Schmidt process for that. Welcome back to it, right? So remember the Gram-Schmidt process, we're going to take these vectors, we're going to choose one of them to be kind of the anchor vector. I will just randomly choose v sub 1, 1 to be the anchor vector. And so you call that anchor vector something else. And since I'm placing that in the matrix P, I'm going to choose to call it P sub 1. So P sub 1 is going to equal v sub 1, 1, which is negative 1, 1, 0. Now I'm going to create P sub 2, which is a second column of P, if you will. And I'm going to do that by stealing v sub 1, 2, the second eigenvector for the lambda sub 1. And I'm going to subtract off the projection of v sub 1, 2 onto the space spanned by P sub 1. That just guarantees I have an orthogonal vector. Doing the work behind the scenes here, we get that p sub 2, which should be orthogonal to p sub 1 now, is -1/2, -1/2, 1. You should take the dot product between p sub 1 and p sub 2 just to make sure, but it is true. When you take the dot product, you get a +1/2, -1/2, plus 0. That's going to be 0. You can also double check that these are still orthogonal to v sub 2, this kind of pink vector up here. I'll leave that for you to double check. Well, great. Now I have these orthogonal vectors, but I don't want just orthogonal vectors. I want orthonormal vectors because I want to build an orthogonal matrix. The only time that A can be decomposed to this format right here is if P itself is an orthogonal matrix, that is, its columns are orthonormal to each other. So let's force those columns be orthonormal by dividing each of them by their magnitudes. All right, these are the normalized versions of those vectors. I did a little trick in there. Remember when we got the vector p sub 2, which is orthogonal to p sub 1 and actually technically to v sub 2, we got down to a -1/2, -1/2, 1. Well, if that vector is orthogonal to p sub 1 and v sub 2, then a multiple of that vector is still orthogonal. So I just multiplied that vector by 2 to get this without fractions so that normalizing was a little bit easier. Now let's go ahead and build the matrix P and the matrix D. And there we go. And by the way, because P is an orthogonal matrix, A can be decomposed into P, D, P inverse, which is the same as P, D, P transpose. It's a much easier computation. Now, while I'm not showcasing any type of application involving this right now, it is incredibly powerful to be able to orthogonally diagonalize a matrix when it comes to computational technology. All right, that's it. That's all I have for this video. In the next and final video, when it comes to diagonalization of symmetric matrices, we're going to talk about the spectral theorem and decomposition. It's spooky.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.